Here we go. The volume of a box is given by this polynomial in standard form. We know that one of the sides has this linear binomial as a side. So what we have to do first of all is factor this standard form polynomial. So it starts out negative x cubed minus x squared plus 6x. And what I notice about this is that there is a common x that can be factored out of all three terms. So if you factor out a common x, you'll get negative x squared minus x plus 6. Next, if we want to factor this quadratic trinomial, it's hard to do with this negative in front. So I would like to factor a negative out of all three of these terms in the quadratic trinomial. So factor a negative out, get positive x squared, get positive x, and get negative 6. Now, this quadratic trinomial can be factored into two linear binomials. X times x is x squared, and we need two numbers that multiply to negative 6 and add to positive 1. So minus 2, positive 3 does the trick. Now, here's the tricky part. See this x minus 2? Doesn't that match up with 2 minus x? Except the signs are reversed. Right? So I'm going to take this negative and I'm going to distribute it to this linear binomial, and so we'll get x and then negative x plus 2. And we can reverse those terms, positive 2 minus x. And so now we have three factors here. This one is one of the sides, and so this x would be another one of the sides, and the third factor would be the third side. Now, the next question says, determine the realistic domain for the function. So let's think about dimensions for a box. Is it possible, for example, that this side could be a negative number? Could it even be 0? No. So this side, we know that the domain, or the x values, have to be bigger than 0. Well, now the next question is, what's the largest value for x? Well, let's look at this orange factor here. On this one, x could go as large as infinity, and you'd still have a positive number. This term here, the x, this could get as large as you want, and it would never cause a problem. But how about this factor right here? If x was 10, you'd have 2 minus 10, and you'd get a negative side length, so that doesn't work. The way this works is, as x gets big, that factor 2 minus x gets small. And so we have to make sure that that factor 2 minus x never gets below 0. And so if you added x to both sides, the biggest value for x is 2. So our answer to this question has to be between 0 and 2. Alright, so now let's graph this volume function as a function of x, and then we'll find the maximum. So if you go into your calculator and you go to y equals I have some excess equations in here. I actually entered the factored form because it was closer. I graphed that. But you can graph either equation. And I did a zoom 6 to reset my window. And get a graph that looks like that. Now we said that we need to find an answer between x is 0 and x is 2. And if I look at this graph right here, it looks like there's an x-intercept at 2. So if that's x equals 0 and x equals 2, we need to find the answer in that domain. And the largest value is going to occur at the turning point, that relative max. So we can do second trace to get to the calculate menu, and then we can do the maximum, and we can set a left boundary and a right boundary, and we can guess, and we can find that the relative max occurs at approximately 1.1 and 4.1. So we need to choose x equals 1.1 to get max volume equal to 4.1. And I neglected to put any units in this problem, so we could just write units and units cubed.